The scientists at NASA use intricate equations to model the path of man-made satellites as well as the space shuttle. Often these equations are what mathematicians call rational equations. These types of equations sometimes provide erroneous solutions, and therefore the solver of the equation needs to take extra care. Otherwise, a catastrophe could occur. Hi, my name is Tom Atwater, and in today's lesson, we will be exploring rational equations. Equations involving rational expressions, or fractions, are called rational equations. Every rational equation can be written in this form: f of x divided by g of x, which are both polynomial functions with no common factors, and that's equal to 0. Now, g of x cannot equal 0 because of the fact it would make that undefined. Now, the zeros of f of x are the solutions to that whole equation. When we multiply or divide an equation by an expression containing variables, the resulting equation may have solutions that are not solutions to the original equation. These are extraneous solutions. For this reason, we must check each solution of the resulting equation back into the original equation. Let's try an example of this. Solve the equation algebraically, support your answer numerically, and identify any extraneous solutions. We have x plus 5 is equal to 14 divided by x. To solve this problem, what we need to do is clear the denominators. And what that means is we're going to multiply both sides of this by x. And I'm going to put parentheses around that to make it clear that we must distribute that. So what it gives us is x squared plus 5x equals 14. And then what we do is say that that's x squared plus 5x minus 14 equals 0. And then we try to factor it. And in fact, it does factor into x plus 7 times x minus 2, and that equals 0, which tells us we can set each term equal to 0. And in this case, we get x equals negative 7. And in this case, we get x equals 2. Now, as I said, we need to check both of those, which means this. We take the number 2 to start, and we plug it back in for x. In fact, that does work because we get 7 on this side. 14 divided by 2 is 7. 7 equals 7. You also need to check the other solution of negative 7, and I will tell you right now that, in fact, when you check it, you will get that it does work. Negative 2 equals negative 2, and therefore both of the solutions are correct for the original equation. Let's work another example, and this time it's going to be solve x plus 1 over x minus 4 equals 0. So this time what we need to do is multiply both sides by x minus 4. So when I multiply this by x minus 4, and I'm going to put it up above here, what's going to happen is I multiply it here, and that means that I need to actually multiply x times each of those, which gives me x squared minus 4x. When I multiply the x minus 4 here, it's going to cancel with the denominator completely, leaving me equals 1. And when I multiply the right-hand side by x minus 4, of course, 0 times anything is 0. So I have a quadratic, which I look to see if I can factor it. Well, I can't. So we need to use the quadratic formula. And in that case, when you work it all out, you get x equals, in this case, minus the negative 4 would be 4, right? But that's the b, plus or minus the square root of the negative 4 squared minus 4 times a times c. And both a and c are equal to 1. And that's all over or all divided by 2a, 2 times 1. All righty, simplifying that, it boils down to this. X equals 2 plus or minus the square root of 3, which leads to two possible answers. X equals 0.268, or x is equal to 3.732. Again, we need to check to make sure both of these work, but let me show you another way to do this. We could enter the equation into the grapher. And if we do that, let me show you the graph that we get. We get this particular graph. And that graph shows us that we get two solutions. 3, and it's about 3 3/4, so that would be the 3.372 that I found. And then we get this answer, which is the one that's about the 268 thousandths. So the graph actually supports the solution that we came up with algebraically, and therefore that's another way that you can check and find support for your solution. Okay, let's work an example that has an extraneous root. Solve the equation algebraically, check for extraneous solutions, and we have 3x divided by x plus 5 plus 1 divided by x minus 2 equals 7 over x squared plus 3x minus 10. So to solve this equation, and we want to clear the denominators, I want you to notice that this expression factors into those two factors. So we're going to multiply both sides of this equation by x plus 5 times x minus 2. I'm going to create this on a slide where I have more room. And again, what I'm doing is multiplying both sides by x plus 5 times x minus 2. All right, when I multiply by the first term, 3x over x plus 5, of course, the x plus 5s will cancel, leaving me with 3x times x minus 2. When I distribute it to this second term, this time the x minus 2's will cancel, which leaves me with plus 1 times x plus 5. And when I multiply those two factors times the other side, what will of course happen is they will both together cancel the denominator, leaving me plain old 7. So now I need to distribute the 3x, and so I get 3x squared minus 6x plus x plus 5 equals 7. I need to subtract 7 from both sides, as well as combine the linear x's, so I get 3x squared minus 5x minus 2 equals 0. We should look to factor this, and in fact, we can factor it as 3x plus 1 times x minus 2, and that equals 0. That gives me solutions of x equals negative 1/3, x equals 2. But again, it's important. We need to check to make sure that both of those work in the original equation. If I start with the x equaling 2, and I plug that into the equation, immediately you should see that 2 minus 2 becomes 0, which means that's an undefined term. Therefore, 2 is considered an extraneous solution. So it's not an answer to this. Now, we also have to check out 1/3. I'm sorry, negative 1/3. And As you can see, that would be, arithmetically speaking, it would take us a long time. So I will tell you that I've done that already. And in fact, negative 1/3 does satisfy the original equation, and therefore that's the answer to that particular rational equation. So I plugged the equations into my grapher, and let me trace them so you can clearly see. Here was one of the graphs, and here's the other graph. And what I want to show you is that they intersect right here, which is approximately negative 1/3. Over here on the right-hand side, I just want to point out that if you were to expand the window, you would see that both of these portions of the graph approach the x, or the asymptote, the vertical asymptote of x equals 2, but in fact they do not intersect with each other, and therefore the negative 1/3 is our only solution. The next thing we're going to do is work an application problem. So let's take a look. We have how much pure acid must be added to 50 milliliters of a 35% acid solution to produce a mixture that's 75% acid. Well, of course, the first thing we need to know is how much pure acid is in this. And if we know that the concentration of acid is going to be equal to the amount of pure acid divided by the total amount of the mixture. So when we look at the information we've been given, we know that we have 35% of a 50 milliliter solution. So we multiply those together, and we know that we have 17.5 milliliters of pure acid. If we let x equal the amount that we need to add to the 17.5, that means we would have x plus 17.5 milliliters of pure acid. Now the total solution has been increased. It was 50, but we just added x milliliters of acid to that. So the total mixture is x plus 50, and that has to equal a concentration of 75%, or in other words, 75/100ths, 0.75. Again, you could solve this numerically by, multiplying both sides by x plus 50. However, let's solve it graphically. And that means that into the grapher, I plugged the two equations, the one that was the actual rational equation, and then the other equation would have just been y equals 0.75. And this was my result. And as you can see from the result, it's intersecting at 80, 0.75. So what that means is that the amount that we have to add is 80 milliliters, and that would give us a 75% solution. So that's a good way that you can use graphs a little bit quicker to solve rational equations. Alrighty, let's do another application problem. Stewart Cannery Company will package tomato juice in 2-liter cylindrical cans. Find the radius and the height of the cans if the cans have a surface area of 1,000 centimeters squared. Well, let me remind you that this 1,000 centimeters squared, that we know that 1 liter equals 1,000 cubic centimeters. So that's the relationship between those. And therefore, a 2-liter can is going to contain, of course, 2,000 cubic centimeters. All right, I need more space to work this problem out, so let me go to a blank screen. We have two formulas that we're going to work with. We have volume and surface area, and we also, of course, have the radius of the cylinder and the height of it. The two formulas that relate these, we have that the volume is equal to pi r squared times h. We know that that's going to equal, because it's 2 liters, it equals 2,000, in this case, cubic centimeters, but I'm not going to use the units. I'll reintroduce those at the end. Surface area. The formula for surface area is 2 pi r squared, and that deals with the top and the bottom of my cylinder, plus 2 pi, whoops, I want to put an r next, so it's 2 pi r times h, and that deals with the side of my cylinder, and we know that that surface area is to equal 1,000. So now, what I could say is, in my top equation, I could solve for h, and h would be equal to 2,000 over pi r squared. And let me write that because we want to make sure. What we're going to do now is substitute that for h in our surface area equation, so that what we get is that 2 pi r squared plus 2 pi r times 2,000 over pi r squared equals 1,000. Well, of course, this is another rational equation, which you could solve algebraically, but it's easier to solve this graphically. Entering the equations into the grapher yields the following graph. Here we go. And it shows that there are actually 2 points of intersection. The first one that I got onto the grapher was this one right here, which is represented by the 9.65, etc., comma, and of course we would expect the 1,000 because that's the surface area. So that's the first solution. A second point of intersection occurs right here, and that's when r is approximately 4.62. So there are two possible can sizes. One could be, and I'll pick this point here first, r is equal to 4.62 centimeters, and h is equal to 29.83 centimeters. My other solution would be that r equals 9.65 centimeters, and in that case, h would be equal to 6.83 centimeters. All right. Well, you know what? Now it's time for you to try a problem. So here it is. The Drake Cannery Company will pack peaches in half-liter cylindrical cans. Let x be the radius of the can in centimeters, and I want you to express the surface area, S, of the can as a function of x, and then find the radius and height of the can if the surface area is to equal 900 centimeters squared. Pause the video to work on this problem, and when you are finished, restart the video to check your solution. Welcome back. Let's find out how you did on this problem. The important pieces of information are, of course, the half of a liter cylindrical can, which would translate into 500 cubic centimeters. The other important numerical piece of information is that the surface area is to equal 900 square centimeters. the other piece of information is that I actually use x as the radius of the can. All right, so you're going to deal with the same formulas we had before. So let me write those down. We have volume is equal to pi r squared h. And that's the half liter, or in other words, 500 cubic centimeters. The other formula for surface area is equal to, surface area is equal to 2 pi r squared plus 2 pi r h. And in that case, we were told the surface area was to equal 900 square centimeters. So once again, let's make a substitution where in the first equation up here, we solve for h. H is equal to 500 over pi r squared. We're going to take that and substitute it in for h. So what we get then is pi r squared h. Nope, I'm sorry, that's the wrong one. I was taking the first equation. We're going to take the second equation, 2 pi r squared plus 2 pi r, and now we're going to substitute for h, 500 over pi r squared. And that equals 900. Now, plugging that into the grapher, we would plug in y equals 900, and we would plug in y equals the 2 pi r squared, 2 pi r, 500 over pi r squared. And solving it graphically, we see this. Again, we have two possible can sizes because we got 2 points of intersection. Here's the first one, when x is equal to 1.12, etc. And of course, we know that y is equal to 900. The other one happens over here. And you can use the grapher to find that, but I will write down the possible answers are x equals, and we're going to round off to 2 decimal places, 1.12 centimeters. And in that case, and that's the radius, the height would be 126.88 centimeters. Now, for this other point, we would have that x is equal to 11.37 centimeters, and the height, h, would be equal to 1.23 centimeters. So I hope that's the answer that you got when you worked out that problem. Now, in this lesson, we explored rational equations and their solutions both algebraically as well as graphically. Be sure to work the exercises that your teacher assigns, and we'll see you next time.